let's make a start. This is, oh, come in, yeah. This is the last week, and I'm sure you're all really tired and thinking about exams and things. Yeah, on the last lecture, we'll go over a little bit what you can expect on the exam, just a bit at the end. So, and then I think 2 tutorials are being planned for you where there'll be a tutor to go over any things that you find unclear. I think they'll be announced a bit later on. Boris has just indicated that tutorials will be made available for students during the STUVAC. So we're going to finish off magnetism here, and hopefully it'll be a bit more sort of interesting than too many equations and things. So remember we talked about diamagnetism last time, and we learned that that was due to the orbital motion of the electrons around the atom, and that in the presence of a magnetic field, that motion, which you can think of as a current, induces a magnetic field that opposes the magnetic field that the material is in, and that causes some of the magnetic field lines to be excluded from that material. So this is a picture of, you probably all know about, levitation by superconductors. I think in first year you look at the Meissner effect, and the lecturer shows you how a little magnet can sort of be levitated above a superconductor. And this is some results or some rather more impressive sort of levitation here. This, it hasn't been done here at the Highfield Magnetic Laboratory in the Netherlands, but on their research page, they talk about this experiment. And you can see here it's a huge Sumu wrestler here being levitated on this magnet. And underneath here is a supercomputer, which is, of course, the ideal kind of diamagnet where all of the field lines are excluded from the superconductor. So you can see that he's really, very heavy, and this is, quite interesting and quite impressive result. But what's also interesting is that you can also levitate with just diamagnetic materials. It doesn't have to be superconducting material. From this same laboratory here, they have managed to levitate a frog, because as you know, all materials exhibit some diamagnetism, and a frog is no different from a material, such as wood, plastic, me. So the frog can also expel some of the magnetic field lines from it. And so what it's in here is a magnetic environment. And I'm just going to try and play this for you. So you can see it kind of just floating around there. It pushes off the sides occasionally, but it's levitating, quite nicely there. So, diamagnetic materials can also levitate. Okay, so that's the point I want to make, since we're talking about diamagnetic materials. Also, this is another example where diamagnetic materials can stabilize a levitation. Okay, so it's slightly different. So, for example, here, what you have is a magnetic material. Okay, this is magnet, and you have 2.5 meters above this, so way up there in the laboratory, a very strong magnet that tends to lift up this magnet from far below. And there is an effect that says, when you have that situation, you know how you've got a magnet and you try and pick something up, the bit of metal will either jump up to the magnet or it will stay down. It doesn't like to hang halfway. So that's a special effect. But if you have a diamagnetic material around this magnet when it's being suspended, then it's possible to stabilize it. There'll be a local sort of energy minimum there, and these lines, the field lines of the fingers, due to the diamagnetic effect, will prevent the magnet getting too close, so it can be held stationary. Okay, this is called diamagnetically stabilized levitation. Okay, it's a relatively newly reported, since, probably 10 years or so, relatively new, and they also can hold a magnet in the center of a diamagnetic material that's also subject to a magnetic field. Okay? So that's 3 kinds of levitation that people are able to do. So this is just a slide from last lecture. Remember, we derived the susceptibility for the case of diamagnetism in an atom. You can also derive that classically, and there's 2 slides here on how to do that, and I'm not going to go through it, but you could go through that yourself. Okay, so the working is here. I think it's fairly straightforward. It's done just using classical mechanics here. You've got the angular acceleration and so on. So you can do that yourself out of class, I think. It's quite instructive. Okay, so now we want to, last lecture we looked at magnetism in single atoms. Now we're going to look at them in a solid. Okay, so remember the kinds of materials where we find diamagnetism is in those where we have the angular momentum, spin momentum, and the total angular momentum is 0. So, for example, like noble metal atoms where the shells are completely filled, so there are no spins available. And that which we derived last lecture for the diamagnetic atom holds very well for describing these kind of materials. The only difference there is we've multiplied it by Z, the atomic number. Okay. So there's 2 other sorts of susceptibilities that we have. Okay, as I said before, all materials exhibit some diamagnetism, but it's a very small effect. Okay, and if you have other kinds of magnetic effects, then that's completely overridden. So, for example, if we've got a metal here and we have conduction electrons, that are free to move around the lattice, then they cannot be described by this kind of approach. They are described by this Landau susceptibility, and that's equal to 1/3 of the Pauli susceptibility, which we'll derive later on, and negative, okay, because it's diamagnetism. So we're going to derive this later on, and this is what it's equal to here. So I think from one of your assignments, or it could be a quiz, you were actually asked to work out the Pauli susceptibility. So here we can see it's equal to mu b squared and mu 0 times the density of states at the Fermi level. Okay? So we'll see how to get that. Also in solids, we're talking about paramagnetism now. If you have a d electron in your crystal, okay, with its various electron orbitals that look like that, if that atom, for example, it might be an iron atom, depending on the kind of environment that it's in, these levels of the d electrons can split into 2 different kinds of configuration. If it's in an octahedral configuration like that's shown here, for example, you've got the iron here, and then you've got 4 neighbouring atoms. They could be oxygen atoms in the plane of it, and then one above and below. That's called the octahedral environment. Then you get the splitting of the state into 3, this degenerate level, into 3 states down here and 2 states up here. And for the example here, we have iron with 6 electrons. So we fill those states lowest level first, put one here, one here, one here, one here, one here. Remember, they like to be all in one orientation. And when it's all filled up to 5 electrons in these states, then we go back and put one in the lowest state with the opposite spin there. And so this kind of complex will exhibit paramagnetism because you can see here we have unpaired electrons. Okay. And remember the example we had for praseodymium where we had the F states and there were 3 electrons in the F states. It can be, depending on what environment that praseodymium atom was in some solids this atom donates 2 of its S electrons and 1 of its F electrons. So in that case, we only have 2 F electrons in about the praseodymium atom. And so the working that we did before to determine the spin and the angular momentum, in this case, is slightly different. And you can figure out, remember before we found that J equals 4? In this case, okay, it's also equal to 4, but you obtain it in a different way. In this case, L equals 5. So you can do that. You've got 2 F electrons, and then you just follow Hund's rules for filling, and you should be able to find L equals 5, spin equals 1, and then remember, because it's less than half filled, J equals L minus S, so you get 4. So you can verify that yourself. Okay, so let's talk a bit more about the paramagnetism for free electrons. Okay, so if we just consider that, and in particular, we're just going to consider, remember these are free electrons running around and they have a spin associated with them. If you write down the Hamiltonian for them, we get here the kinetic energy term, momentum squared over 2m. And then we have this term here due to the presence of the magnetic field. And this is the spin. Remember, it's either half or minus a half. Okay? And that's just the ball magneton here. So what happens is if you have a magnetic field B, the energy of the system with spin up, if you have spin up electrons, your Hamiltonian will become like this with a plus sign here. If your electrons have spin down, indicated by the arrow here, you'll get minus mu B. Okay? And then we go back to, like, from our very first few lectures. Remember these density of states plots? Okay, remember this? Before we didn't consider spin up and spin down. We just had total density of states G as a function of energy. It had this square root of each behavior. Remember that? Okay, so this is still the case, what we get in the no magnetic field. Except now we've divided them into 2 bits. Those electrons with spin up and those electrons with spin down, and they're just the same. Okay? But because we're splitting the number of electrons into spin up and spin down, we know that the spin up number equals the spin down number and equals the total divided by 2, because we're just splitting the total into 2 pieces, spin up and spin down. So what happens now is when you are in a magnetic field, these electrons will move upwards in energy by mu B. Okay. Now, so what happens is when this energy is pushed up, you get some of the electrons in this empty area here going above the Fermi level. What happens is that they get transferred into, they flip their spin and they turn into spin down electrons. The Fermi level stays at the same place, but this whole density of states moves downwards by mu BB. Okay? So we have flipping of some of the spins when we're in the magnetic field. And, okay, it says here there will be G at the Fermi level mu BB over 2 fewer spins. Okay, how did we get that? This is the number of electrons that flip, and it's just again approximated by this rectangle here. Okay, so we have the height is the density of states here, and because it's spin up, and we've got the total density of states here, we have to divide it by 2 because we only want G up, and then that's the height of the rectangle, and then along the energy axis, this is where we get the mu BB. Okay. So this is again just continuing on from that diagram. So as I said before, the spin-up electrons are pushed above the Fermi level, and in order that they can lower the energy of the system, they flip their spins, flipping their spins, and they become spin-down electrons. And the total number of electrons that flip, that is the area of that rectangle that I just described, is just like I said before, only here we've got just the density of states of the spin-up electrons instead of the total, because that's just exactly half of the total. And therefore, we can work out the magnetization of these electrons in the presence of a magnetic field just by here. The number of spin-up electrons, remember that rectangle that was pushed above the Fermi level, minus those that are pushed down. And what you get is this here. I'll just, maybe I'll just write that one out. Just so we had defined the magnetization equals to, what do we have here? A number of spin-ups minus number of spin-down, mu B, okay, per volume. And we know that the number of spin-ups, we know that we lost those number, okay? So we lost mu up, sorry, G up mu BB, where that G up is at the Fermi level, and the number of spin downs was G down at the Fermi level, mu BB. Okay, and then we know that G up at the Fermi level is equal to G down at the Fermi level, and that's equal to G over 2, the total density of states on 2. So you can substitute that into being G E at the Fermi level on 2, mu BB, minus G down, which is equal to G at the Fermi level over 2 mu BB. All these will cross out. These will be added. So you end up with, there's a mu B outside here. So there's a mu B outside here, mu B on volume outside there. So mu B over volume, B over volume. Is that right? Oh, the volume has disappeared. So because we divide magnetization by volume, so we can get rid of that. Okay? So let's put this back up. Yeah. they are just different ways the electrons are. This either spin up or spin down. You can think of it in a magnetic field. There'll be some electrons with the line spin up and spin down. So they just have different spins. It's either a half or minus a half. Okay. So, yep, this is the important equation that we just derived in that way of thinking by looking at these density of states and knowing that they shift up in the presence of a magnetic field, they flip their spins and move down. Okay, so just a quick look at the kinds of materials that exhibit certain kinds of magnetism. You can see there's not really very many perfect antiferromagnetics. We only have chromium here. We have the usual ferromagnets that we have discussed before, iron, copper, nickel. Many of them, of course, are paramagnetic, and diamagnetics are here with the filled shells in particular. Okay? And of course, when you put the materials together, you can get all sorts. Magnetism is a really complicated field of condensed matter, and we just sort of touch a little bit of it here, but it's a really quite a big field all on its own. I wanted to show you, you know, what the density of states and the band structure of magnetic materials kind of really look like when you actually calculate these things using state-of-the-art approaches. So what are the state-of-the-art approach? They're kind of quantum mechanical calculations. Some of you from chemistry may have done you know, quantum chemistry calculations already. I don't know. One of the most popular and widely spread approaches is density functional theory, which we may talk a little bit about. But remember, we looked at the band structure, and we had, you know, talked a lot about free electron-like behavior. You can see that real materials, in particular, I think this one's got iron in it. It's some, it could be just plain iron. I've forgotten where I got this from. It could be just pure iron, or it could be iron oxide. I don't know. But what's the point? The point is, in addition to, normally up to now we've only looked at bands. Okay, we haven't looked at spin polarized bands due to magnetism. In this case here, we've split the electronic density up into spin-up electrons and spin-down electrons. And for materials that are non-magnetic, these lines will just lie on top of each other, and we don't even need to think about you know, spin-up or spin-down, like aluminium, magnesium, silicon, diamond. So you don't need to do spin polarized calculations. But for certain materials you do, and you can see that the electronic bands are really quite different. For example, here, these are of one type of spin, spin up, and the blues are spin down. Okay, so you can separate your electronic structure and look at just one particular kind of spin. And the corresponding density of states, remember we've looked at density of states before? This is the normal way people kind of plot it. If you've got two different density of states for your different kinds of electrons, spin up and spin down, you normally, on the positive axis, have one kind of spin up or spin down. In this case, the spin up, and the spin down here is shown like in the negative axis. This is the usual way. Sometimes people put them both on the positive axis, but this is the usual case. What's shown here is, you can see that there's a grey shaded region. That will be the total density of states for the whole number of electrons in your system. But you can also project out just the contribution due to the iron atoms. You can select any iron atom you want, and you can look only at the contribution due to the iron atoms, which is shown here, the red, and the blue here. Okay, I just wanted to show you that. So, you know, you see what it looks like in sort of research kind of environment. Okay, now I want to just talk briefly about the Heisenberg Hamiltonian and the Ising Hamiltonian. I think you've done a lot of, I don't know if you've done a lot or a bit of this in your statistical mechanics, so I'm not going to go over it too much. You've probably know much deeper than what is going to talk about here. I just want to say that these kind of models are, you can use them in magnetism. Usually, what you usually do is, well, the state of the art, what you would do is you would use this Hamiltonian. I'll show you an example very briefly. These are J's. These are the interactions between atoms with particular spins, and you calculate those interactions from these kind of quantum mechanical calculations to get really accurate ones, okay? So what have you got? You've got your Hamiltonian. You have spins on one site and spins on another site interacting here. This is your exchange energy. Over here, you've got the contribution due to the magnetic field here. When the spins are aligned, for example, you might have a positive value of J, depending on your system. Don't always have in the reality. You can calculate this thing. And so this is the interaction energy, which I've said here. If you just forget for the moment this term here, okay, that's just due to the magnetic field, and look at this interesting thing here. If you can, this has made the approximation that the J is independent of the particular atom site, because you can see it's just lost its labels, if you like. So in the approximation that J is going to always be the same between the different atoms, you can just treat it as a constant. That's just what's done in this red box here. Okay? But these are going across all the different atoms in your system. Okay, double counting to avoid that half there. So what is this exchange interaction? Okay, it's a consequence of the Pauli exclusion principle. You've got your spins on your atoms. It might be spin up, it might be spin down. The spins can also be canted. Don't have to be up or down. In the simple case here, two possible arrangements. You've got your spin up or you've got spin down, like ferromagnetic or antiferromagnetic arrangement here. And in reality, these will have different energies, right? If you calculate the total energy of your system for your spins aligned upwards or aligned downwards, that will give you slightly different energy, okay? And it's that energy difference that defines the exchange energy, okay? So you can calculate actually the exchange energy. You do all the spins up, and then you calculate the spins down, and it'll be slightly, usually it's on the order of MeV difference, okay? But you can get these energies from such calculations. And it's assumed, and it probably actually is, although not always, but in this model, yes, short-ranged, and you only need to take into account, two interactions. Spin here, interacting with the spin here. Okay? But you can imagine that depending on your material, the spin interaction might change as a function of distance. It might also change, if you've got three atoms with spins interacting, okay? If I've got an interaction between two atoms here with spin, and I bring another one close, this interaction might change. So you can also take into account that kind of possibility by making your model a little bit more complicated. Okay, what else have we got here? Okay, this is the same thing, the same kind of Hamiltonian, but what you can add here is another term. If you know your system has a preference for spin up to be perpendicular, okay, to the plane that you're considering, you can sort of code in or describe that preference, if you like, by some anisotropy energy here, okay? So it will give you a lower energy when your spins, for example, are in the Z direction. You can play with these. These are only models, okay? It's just a model Hamiltonian. You can also say, okay, in my system, I know that the spins are going to be aligned along the X, Y, and Z kind of axes. You can describe it using that kind of Hamiltonian, if you like. The Ising one here, this is where you have forced the spins to be simply either up or down. Okay, so this is a Ising one, where you've got just spins up or down. Okay, I don't want to spend too long because I know you've done this already. Yeah, just a little bit more here. While we are talking about, the interactions of spins on neighboring atoms, it's good to put a name to that. So in these Heisenberg Hamiltonians, these Ising Hamiltonians, you are dealing with direct exchange. It's called direct exchange here, okay? This is Ashcroft and Merman, for those of you that are reading that. So it's when you've got the ions close such that the wave functions are overlapping, as indicated by here. You can see they're overlapping, so they're interacting directly with each other, hence the word direct. There's another terminology called super exchange, where you can see quite clearly, I think, what that means. It means these atoms with spins are interacting with each other, but via a non-magnetic atom, okay? So, but you can still see that these atoms' wave function is interacting with the non-magnetic atom, and so is this one's, and it's through this atom that the interaction occurs. The last one that I talk about is called indirect exchange, where, again, I think the picture is nice. You can see here you've got your magnetic ions here. They are not directly interacting, nor do they have an atom between them, but these little arrows here indicate conduction electrons, so they are still affected by each other, but the interaction goes via the change in the conduction electrons. Okay? Indirect exchange. That's all I want to say about them, just so that you've heard about those kind of interactions and know what they mean. Yeah, I just wanted again to show you some kind of research that's being done using just one example of, many that I just sort of found for you here. It's again using this kind of recent work. What they are looking at here is just a sheet of boron nitride. You can see here it's got boron nitrogen or other way around, I don't know. And what they are doing is they want to be able to predict the magnetism of this sheet of boron when it's doped with manganese atoms, okay? So experimentally they can do that. They can put manganese atoms on their boron nitride. They will know, I don't know myself where it goes, but they will know which site it occupies. It may replace one of the borons or one of the nitrogens, or it may sit in the hollow site. It looks to me from this study that they are considering exactly replacing atoms. That's called substitution adsorption. So you are substituting one of the atoms of the host with your new species. So what they've got here is this kind of Hamiltonian. I'm not going to go into it, but you can see it's got various interaction parameters, J, okay? Not just J between two atoms, IJ, it's also taking into account the interactions of three atoms, IJK, and it's also taking into account the interaction of four atoms with each other, because that affects your Hamiltonian, it affects your energy as well. And normally what you do is you can keep considering more until your Hamiltonian doesn't change, okay? So you can see here, this shows an example of what they are doing for taking into account three interactions. You've got two of your manganese here and here. This is just one example. And then you are putting the third one, for example, here, and you're calculating the interaction energy, okay? Spin up and spin down. And then you're taking that away and trying this side a bit greater distance away, and again calculating the interaction between this kind of triangle shape, and so on. You are going further and further away from this little dimer. And there's other sites, of course, that you can consider here, in the back kind of it, here, 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 here. And then you can plot out your obtained J's as a function of distance here, okay, you know, as we've gotten further and further and further away. And so these are the J's that you've calculated that you can then put into your model, Hamiltonian. And then what they've done here is they've been able to predict, firstly, whether and what kind of magnetism this material will have, and as a function of temperature. And they've done various curves here. I think they've run some Monte Carlo simulations using this, and these are for different sized Monte Carlo simulation sizes, I think here. Anyway, I just again want to show you an example in magnetism where they are using these kind of approaches to do research. A little bit more about research, this time experimental. These are really nice results from a very well-known group in Germany. I have to try and remember what they are doing here. Okay, so what we've got is, what is it called? It is called non-contact atomic force microscopy. I guess some of you know about atomic force microscopy. It's where you've got a tip and it's running across the surface of a material, okay, and it adjusts its height according to the force it feels somehow from the atoms. And you get these patterns, okay, which reflect the position of the atoms on your surface. So these spots, you know, they can correspond to nickel or oxygen atoms. In this experiment, in this structure, you have nickel atoms, which are grey, and you have oxygen atoms, which are either green or red. But in the real material, these oxygen atoms have different spins. Some are up and some are down. But when you do this experiment and you plot here the corrugation of where the atoms are, you can see that the peaks correspond to the nickel, dips correspond to the position of the oxygens. You cannot distinguish the spin of these oxygen atoms, okay, because they look just the same height. So you can't get any magnetic information. But when you do this experiment, this is a spin-resolved image using magnetic exchange force microscopy. So there is some you come here with, you can see it's got a little spin on the tip. This one has no spin on the tip. This is kind of usual, but you can create a tip, like where you scan, that's got spin on the tip. Like you might use, I don't know, you know, it's an art creating the tips of your materials as well. But you can see quite clearly difference between the height of this oxygen atom to this oxygen atom. So you have been able to resolve that these oxygen atoms are of different spins. You can also see that the difference between here and here is really small, 4.5 picometers approximately. So that's 0.01 of an angstrom. So these experiments are really, really you know, quite difficult to do, and you have to cool down your sample to, I don't know what temperature, but very cold temperature to get that kind of resolution. More experiments, which are really nice as well, again from the Wiesendanger group. Spin polarized scanning tunneling microscopy. Who knows about scanning tunneling microscopy? Yeah, it's a really big field. It's one of the best ways to find the atomic structure of a surface, usually combined with theory, because often what they see, such as here, they don't really know what everything corresponds to. So in the scanning tunneling microscopy, what you do is you come along with a tip, but in this case you are putting a current from the tip to the sample, and you can measure that current, and the current will be different depending over what atoms you are going over, and you will see this kind of, again, corrugations. So what does this experiment show? They've stuck 3 together, apparently, and let's see, it's a, so what I want to say is normally scanning tunneling microscopy is not done spin polarized. I mean, only special groups have spin polarized, and so normally you don't get spin information, but you can also do it spin polarized, and you can get magnetic information. So this is of, what is it? They're putting iron on tungsten. So you've got a flat tungsten 001 surface, and you're putting a layer of iron. You want to grow it flat on the surface. But, you know, when you grow stuff experimentally, it's never perfect. And you can see the regions where it has grown perfect. It's nice and flat. You can also see they think that these are either add atoms of extra iron, or they can also be defects, like holes in your layer. So vacancies and adsorbates, okay, vacancies and adsorbates. And you can also see here, this really big area here, which they know is a double layer of iron islands. Okay, so it's not perfect. In fact, you've got another layer of iron growing on that. Okay, so I want to make you aware of those kinds of experiments where you can look at least the magnetism of surfaces. And okay, one last one here. Here again, it's spin polarized STM, and you are growing islands of 2 sorts of material. If we look first at the top layer, we are growing cobalt islands on something. Now, what are we growing it on? I don't know if I can remember. Sorry, it's probably written down here, but we've grown cobalt islands and iron islands on some substrate here. If we just look at the first one, they have found that the spin orientation in these 2 islands are different. So, for example, in B, the spins are all up, and in the other island, we have parallel and anti-parallel spins. Okay, and then on the basis of these 2 diagrams, you can make some differential plots so that you can see a little bit more clearly what's going on. The details of that I'm not too sure about, but this plot's made from those 2. The same thing here. In this case, from the experiments, they can determine that one of these islands at 0 Tesla, oh, hang on, what are we doing? Yeah, 0 Tesla, it's just have your spins up, and then you you apply magnetic field, and you can switch the magnetic behavior of the material. And I think in this case, it's somehow, you see, you don't have to have just spin up. You can have spins changing over distance, okay? So magnetism is quite complicated when you're looking at real surfaces. I'm not sure if we'll get to that, but in the notes I've got something about the energetics of having spins canted versus over distance or just flipping straight. And it's more energetically favorable if they actually do change spin over a distance rather than just flipping. And this kind of area, so as a function of distance here, this kind of behavior is what we call a domain boundary for the spin. So the spins don't just flip like, you know, in your sort of standard picture. You have domains with just spin up and spin down. Normally there's a domain boundary. Okay, what's the point of this one here? The point of this slide is to show that, which you probably know from earlier studies, rather than having just one whole domain of the same spin, it's energetically favorable to create different domains with different spins. Okay? And when you apply magnetic field, this I know that you know already, one of the domains will grow and in the direction of the magnetic field, and the other ones with the opposite spin will get smaller. Okay? And you can also have spin orientations, going all different kinds of directions. The reason for that is that you will get a smaller magnetic field when they are not all in the same direction there. Okay? Let's see what else. So we're talking about these, the areas where you have different domains, magnetic domains, and how they switch from being of one orientation to another orientation. This shows two different, well, these are the same pattern of spins, but one of the changes goes via, this is a defect, it does not go via the defect, and so you have spin up, spin down, spin up, spin down, spin up, spin up, spin down, all the way through. And this configuration, I mean, these domains obviously prefer to be all of one spin. That's why they've arranged themselves that way. So when you go through a position where you've got spins of opposite spins, that costs you extra energy, okay, because it's not favorable. They like to be all of the one spin. Okay. Now this boundary or domain wall, if you like, passes through a defect, and so you get one less of these kind of interactions appearing. And so this configuration is actually more favorable. So the domain wall is said to be pinned at this defect, okay? Because this has a lower energy because it has less of these unfavorable configurations. And this is a technique that people know about. So people actually introduce certain defects in order to control where their domain boundary walls occur, and to pin them, to make them happen. Okay, this is some working that shows you that it's more favorable to have this kind of canted spin orientation. It's called a block wall or a Neal wall, okay? So we've got this Hamiltonian from before, and we've got this anisotropy term here, which says we favour, say, spin along the z-axis. And, okay, we've got a length of wall, as sketched here, called L. And, again, a spacing of the atoms with spins is called little a. And we've got n of them, so L equals NA here. So that's just defining it. So basically, you have a balance. To change spin will cost a certain amount of energy. So you can say that, okay, over some length period, the spins will change from up to down, okay, and with each n, each n, your angle will change by pi over n, because, it has to go from here, like 180 degrees, okay, so that's how you get the pi here. So each spin will change by just this delta angle as it goes over. So now we have the spins are vectors, and so we are just doing the dot product of the two spins here. knowing that the angle between two of the adjacent spins is equal to pi over n, this is how we get this expression here. Okay? And then if we just use a small angle approximation for cos. So we're just putting cos of I minus cos of j is just equal to the delta cos. So this is an expression that tells the energy cost for one of the spins being rotated by that little angle. Okay. So, yeah, we have this expression from before, okay? And, you know, you can see that it has the lowest energy if the cos goes to 0. But there is another cost that we have to consider. As I said before, it's a balance between two costs. The other cost is what is called energy stiffness. Now, I'm just going to give you the formula for it here. I'm not going to bother deriving it. I'm sort of at the end of magnetism. But it's in the notes. So you can define the stiffness per area, meter squared or angstrom squared, whatever, and per unit cell. Okay, so this is the stiffness per unit cell. And so basically, you will have two energy costs that can go into the description of your energy. And I'll just jump to that because I'm running out of time. I'm sorry, I'm running out of time already. So what's the point? You have the anisotropy energy, and then you have that other energy that I talked about before. I'll skip that. You've all seen a hysteresis curve before. But what I want to do is jump down to the last slide and show you that you can define an energy per volume in terms of the two contributions, the two energy costs of creating the domain wall. Yeah, that wasn't very well explained. I'm sorry, I'm running out of juice. But yeah, I'll put these notes up and you just read through that, okay? And please, again, email me if you've got any questions at all about assignment number 2, about, yeah, about anything.